Good morning, good afternoon. This is Dr. Rudy Shankar. I'm very excited about making this presentation on renewable energy and opportunities in India, especially so in India where it's expanding its renewable energy portfolio. And I think there's some great opportunities for young minds like yours to be involved in this enterprise. A little bit about my background. I have more than 40 years in the energy field, working as recently as a vice president at Tennessee Valley Authority, which is a large utility based in Tennessee, United States, but it serves 7 other states surrounding the state of Tennessee. So it's a very large utility, and it's been a model of utilities for people around the world. In fact, the Damodar Valley project in India was pretty much fashioned after TVA. So I was very proud to be associated with it for many years. I was also the chief executive officer at Signatech Systems, with a startup company. Before that, I was a program manager at the Electric Power Research Institute for many years. As you know, it's a world-renowned institute for energy research, and we operate globally. And I worked with one of our partners, NTPC in India, as well as many other utilities around the world. I got my PhD at the University of Delaware and my MBA at Queen's University. And I'm very proud to say that I got my Bachelor of Technology with honors at IIT Delhi. It was one of the earliest batch, and I'm very proud to see the tradition that the IITs have set around the world. So my talk is going to encompass these 4 areas. One is, what is the state of electricity in India, electricity delivery, electricity generation? It is a critical infrastructure in India, as it is in every part of this world. I'll talk a little bit about our department, which trains the energy workforce to be leaders in the energy industry. So we have a very directed mission, and somewhat unique in universities that offer this kind of curriculum. It mixes experiential learning with textbook knowledge. I'll then talk a little bit about the dramatic energy portfolio change. I think India would be very proud of when they achieve this change of more renewable energy on its grid than fossil-based fuels very shortly within this decade. And finally, training an energy workforce. I know I won't be able to take questions and answers, but I will really enjoy talking to you through email or any other means that you're thinking of. Just a footnote, a lot of this presentation was based on a paper I wrote for the Energy Central, which is a magazine that is distributed in the United States and all over the world on power generation trends in I think back in March of this year or before that, I forget. Here's a graph that I wanted to talk a little bit about and the role that electricity plays in development. What this shows is per capita income along the y-axis and time on the x-axis. So you can see the time starts from sometime from the Great Depression, 1929 to present day. And the vertical scale is the GDP in log scale. So you start out with 1,000, jump to 2,000, and so on up to 50,000. You can see in the second half of the previous century, Western Europe and the United States had a rapid expansion in GDP. So they were becoming more prosperous. Whereas, for example, in Asia, China and India were pretty much flat during those times. China was a little more dynamic, but India was truly flat for most of the past second half of the past century. But this rise in prosperity that was experienced during World War II in Western Europe and United States is now being replicated by China and India. Not to the same level, but you see the same very dramatic increase in GDP. And the one common theme between both of them was there was expansion of electricity in Europe and in the US during this time, during the last century. And now we're seeing this happen quite dramatically with China and India. So the point of all this is electricity is a key factor in prosperity. If you were to look at the largest generators of electricity today, number one is China, number two is USA, and next close behind is India at third position. So this is really where electricity is going to play a role, not only in prosperity, but as I'll talk about later on, looking at the clean energy portfolio that we need to have to combat climate change. This is the India installed electricity capacity in 2019, a couple of years ago. And like most countries, we have a diversified portfolio. But you can see there's a large portion of the pie which is dedicated to coal, which is a cause of a lot of climate problems, which is starting to affect India. Polluted cities near Delhi and Mumbai and Chennai are some of the examples of what has been happening. But we also have a pretty diversified portfolio of using natural gas, diesel, hydroelectricity. We have quite a large portion of the 45.4 gigawatts. We have a small portion of nuclear and quite a number of renewables. And this is somewhat surprising compared to other big countries. Our capacity for renewables is roughly 25% of the total portfolio. And if you were to look in more detail, what is the constituents of the renewable portfolio? You have wind and solar are the major contributors. And we have small hydro, waste to power, and biopower are smaller fractions. Keep a note of this slice of the pie as we go forward from 2019 to the following decade and the end of this present decade. And so I mentioned about global warming being a challenge. And this is a graph which is right out of COP-C, which was looking at different scenarios for global heating if we were to not do anything. And that is this trend. So that will cause global temperatures to rise between 4 to 5 degrees centigrade, and this could be horrendous at the end of the century. So if I was talking on behalf of my generation, to leave this as a legacy for future generations is very unconscionable, is very criminal, in fact. So we cannot allow this to happen as we progress. We cannot let business as usual dictate. Now, all the other curves tend to want to reduce the global rise in temperature to avoid greenhouse gas effects. Again, for those of you who don't know what those limit mandates are, we want to keep it between 1.5 degrees centigrade to 2 degrees centigrade to pre-industrial revolution levels. That we're talking about no more than 1.5 to 2 degrees centigrade from the 1850s before the Industrial Revolution caught on. So this is a very challenging task. And so all these different slices of the curve are for different pledges. So even with optimistic net zero, we can at best attain 2.1 degrees centigrade above pre-industrial levels. Not good enough, but not bad. But this, again, you have to bend the curve. That means avoid using fossil fuels completely, especially by the big generating countries like China and like India. I think this is where the challenge is. So what has changed in the last 20, 30, 40, 50 years? And this pace of change is different from one country to another. You had a traditional grid where the generation was far away from the load center. And so you didn't have solar on the roof or wind turbines connected to small offices, or for that matter, combined heat and power for small offices. That came to be in the last 20, 30 years, the modern grid, as you can see on the right, is a lot more crowded because you have a lot more assets all over. But more importantly, you have the flow of current, both backwards and forwards, and the grid was really not designed to be able to handle such flows of currents. So this is becoming the modern grid, where a lot of assets are there at what's called the grid edge, that is near the customer sites. And so even in a country like India, which is developing, we're seeing a lot more activity at the grid edge, where the customer could be a business customer or a residential customer, has his or her own generating assets, solar on the roof, for example, or could have an electric car. And India has made a pledge of 50% electrification of cars by 2030 and almost 100% by the end of the next decade. So very aggressive moves are being made. But the story that we have gone through this past decade, 2009 to 2019, the world has not seen a change in fossil fuel consumption. It's gone from 80.3 to 80.2. So this is somewhat disappointing results. But of course, more people are using electricity, and the one piece of good news is renewables have shown the biggest growth from 8.7% in 2009 to 11.2%. So when we had to look at growth of new generation, it's definitely been in the renewable space. And more specifically, it's been in wind and solar. And more specifically than that, China has become the biggest producer of more renewables. They are installing more wind generation, more solar generation, and really advancing much faster. And India is close behind, but not as fast as China is. So even though renewable energy has increased over the past decade, fossil fuels have dominated. That is the bad news, but the good news is renewable energy has increased. And a big part of the reason is because the cost of electricity through renewable energy has dropped dramatically. What we call the levelized cost of electricity has come down for renewables, and I'll get into that in a minute. So if you were to look at the greenhouse gas emissions share worldwide, we emit as a world 50 billion tons annually. That's even difficult to comprehend. Energy accounts for 75% of all greenhouse gases. So what we're doing in limiting greenhouse gases through electricity production and transportation and through industries, cement and concrete making are big industries, and they use a lot of carbon-based fuels. So that's one of the reasons where greenhouse gas emissions challenges are in all these sectors of energy generation, transportation, and industry. And the big three are China, USA, and India. Again, I want to kind of remind you, prosperity depends upon electricity generation, and China and India are definitely the most big users of electricity in the world. And China, of course, has even taken over the lead from the United States. So decarbonization of energy will have an impact in meeting global challenges. And so I think the whole world needs to act in concert, but definitely the three big players, China, USA, and India, can set the lead. And this talk will show that India is definitely, in this coming decade, is going to show a shining example of where renewable energy could be part of the portfolio. So this is where I want to talk a little bit about our program, the Energy Systems Engineering. As I said, we're at the Lehigh University just outside Philadelphia in Pennsylvania. And this is our mission statement: produce a new generation of world-class leaders for the energy industry. And we depend on the learning process to be experiential. I'm the director of the program, and the staff includes people like me who have a business background in energy. So we not only combine textbook knowledge, but we are also able to give you experiential knowledge, which includes not only the technology itself, but how does it work in real life, in the field, as it were. And that's where sometimes there could be a big gap between what is in the textbook to what you can get in the field. So this is really important. And one way we make sure this learning process is very realistically based, we involve the industry in many ways, not only as part of our advisory council, which basically tells us how to guide our curriculum to better meet the needs. But also, instead of a thesis, we have what are called capstone projects, which are sponsored by the industry. So even the most important part of your learning is done through not writing a thesis, which could be somewhat theoretical. This would be very much industry-based, industry needed, and you'll have industry project managers working side by side. So there's no pretense as to why we involve industry, is because we train you for the industry. And by having this proximity of industry with the program, we're obviously very hopeful that you'll be placed in the industry. And I'll get to that towards the end. So what we offer is a Master of Engineering in Energy. It's a graduate degree consisting of 30 credits. You can also choose to take a certificate in energy system engineering, which is 15 credits. Or you can continue taking courses as you please. And for people who are working full-time, these two options are quite attractive. Although we also have people who take a leave of absence from work to finish this quite quickly, and I'll get to the timeframes. The Master of Engineering program as a full-time student is 10 months. So this is pretty fast, less than a year. You complete 30 credits. There are 18 core subjects taught by industry professionals like me. And so we want to make sure that the core credits, 18 core credits, have a very strong experiential learning component. We've also introduced energy seminars that we invite outside speakers, and we also do a field trip. That's a 3-credit elective, and we highly recommend that the people who come through this program take this particular elective. And of course, the 6-credit industry-sponsored capstone project is one of our highlights. Is one that makes a difference between our master's program and any other master's program. This is very much industry-based, industry-sponsored, and it fits to our mission of developing world-class leaders in energy. So what is the pace of change of those changes in the grid that I talked about? I call them 3 Ds: digitization, decarbonization, and decentralization. It is quite rapid in some places. Even in places like China and India, I would say it's very rapid. It's slower in some Western European countries, but the common factors in every country, China, India, US, Western Europe, is because of the internet, it's very customer centric. You and I as customers have a big say in our composition of electricity. How friendly is it to as far as greenhouse gases are concerned? And this social equity is another factor that's starting to come in, where economic demographics aren't affected by inequities in power generation. So the 3 Ds: digitization, decentralization, decarbonization. It's very long words, but they really mean one thing, and one thing is progress. The world is trending towards this. Having digital data gives you the ability to store energy asset operational and maintenance data for diagnostics, prognostics. You don't have to have people at different industry asset sites. You could have the internet and have centralized experts who could interpret information. This is happening in every field. Energy is no different. The decentralization is really where the source of generation is right there where the load is. So this avoids costly transmission lines that need to be built to transfer the energy from one place to another. And decarbonization, of course, is replacing carbon-based fuels with more environmentally friendly fuels. And those would be renewables, of course, but hydrogen will also play a huge role in this as we go forward. So the digitalization, as I mentioned, is an ability to store information, and you can now perform diagnostics that use advanced machine learning and artificial intelligence methods. In fact, we're doing a capstone project that does involve exactly these capabilities. I will get to that towards the end. Decentralization, as I mentioned, where the load center and the generator are very close together, right at consumer sites. So we have terms like net metering. That is, if you can sell electricity back to the grid as well as consume from the grid. And so these policies that are coming into place are different in different parts of the world. The United States is different parts of the country itself. You could have different net metering policies. And you can also, instead of buying costly power for meeting peak demand, there are entities called virtual power plants. It's a very interesting concept, basically being able to marshal all the solar on the roof, all the storage you have, the energy you may have in your electric car, to basically be a substitute for generating plants, especially to meet peak demands. As you know, meeting peak demands is a very expensive process. So this could be economically a huge savior. And we have a lot of activity in virtual power plants. And we have some capstone projects that involve working on virtual power plants. This is kind of a visualization of a virtual power plant. Is basically getting all the assets through the internet, aggregating it, and through using machine learning and artificial intelligence methods to meet the grid demands, especially during peak times. That's when electricity is very expensive and you need an economic alternative. Of course, decarbonization, as I said, we need to move away from fossil fuels, to environmentally friendly fuels. And this is the guidelines according to the IPCC, the Interplanetary Commission for Carbon, for climate change, and the CC is for climate change, that it has to maintain the temperatures no more than 1.5 to 2 degrees centigrade above the baseline, which is pre-industrial level. Here's a graph from Ernst & Young. They made a presentation about electric vehicles. Again, electric vehicles, right now fossil fuels dominate vehicular transportation. And China and India have made a pledge that, in very short time, they're going to have complete electrification of vehicles. This is very daring, very ambitious, and very good news as far as climate change is concerned. As you can see, our present administration, the US, has also made a somewhat similar promise, but not as ambitious as China and India. Again, this is one of the sectors that needs to be decarbonized, and we have plans at least. Of course, plans are different from reality. Let's see how real we are. But definitely China and India are betting on electric transportation as the future. I wanted to talk a little bit about this. This shows the generation capacity of India today, 2019, to where it's going by the end of this decade. It's 9 years from this year. You can see, first of all, it's going to more than double its capacity, 356 gigawatts to 830. And like most advanced countries, at least countries with advanced grids, you have to have a diversity of electricity generating resources to manage your risks. So we have, at this point in India, the majority of electricity is through fossil fuel, in fact, coal. Gas is a small fraction. That's the gray pie here. The black pie is coal. So between coal and gas, the major carbon contributors, more than 50% of our electricity is generated by carbon-based fuels. The ones that are light green or green, they're all renewable fuels, and the others, which are nuclear, for example, is really, it's green energy, but it's not renewable, is a small but significant fraction of the pie. And I want you to focus on that because we're doing pretty well compared to many nations as far as what our breakdown of renewables is more than 25% of our total fuels. But I think the good news is down the road, the end of the decade, 2030. We're going to more than double. Our capacity is going to increase to 133%. Just the renewable energy portion, which are the green areas here, is more than 50% of the total. That's remarkable. No, not one Western European country, maybe some Western European countries, but definitely not the US, will reach that level. In the US, perhaps a couple of states like California and New York would be at the level where India is. But India's grid will be carrying 830 gigawatts of capacity. Just the solar and wind, these two slices of the pie, in 2030 is bigger, 440 gigawatts, is bigger than all that we generate today. So very ambitious, very good news. And I think more than anything, it requires students like you to join in this energy revolution to make this happen. This is quite different from the way we used to generate energy in the past using centralized generation. Solar and wind are the renewable fuels of the future. And this is where education and training people to get into this field would be very important. So I'll now spend a little bit of time on some details about how solar and wind work. You may know this, but irradiance from the sun causes photovoltaic cells to generate electricity. And because the sun energy is free, you can say that the solar energy is also free because you don't have to pay a price for this fuel. In some places, this fuel is plentiful. India is blessed with very good sunshine. They're just north of the equator, so the sun irradiance is very good. And so it's a question of harnessing this energy and through an inverter, converting it to AC power so that it's able to work on the grid. The AC current is what transports electricity throughout the grid in India or anywhere else. The frequency at which this energy is transmitted is at 50 hertz in India, 60 hertz in the US. The equivalent circuit, if one were to show a cell, is given by this current source with a zener diode and a parallel resistance. So the load is represented as a series connection. So each cell and each module is basically a replication of each cell. And so that's how you accumulate voltage and current in a solar panel. And you design it to operate at this point where you have maximum power, and you can go through the math to see why that is the case. So when you stack up these cells, you build up the capability of the solar panel as shown in the cartoon about here. So each of them performs in its own way, and you build this up, and you have then an array that can generate 200, 300 watts. That would be one single panel. And so you stack up these panels, you can generate quite a lot of electricity. Another way to harness solar power is through what is called concentrated solar. That is, you place mirrors reflecting the sun's rays in a focused or in a consorted way to boil water Nowadays, instead of water, they use molten salt because it has a high heat content capability, and you can operate at higher temperatures and get more efficiencies out of this. So that coolant here then is used to turn a turbine, and that turbine then generates electricity when it spins in a magnetic field, which is how electricity is generated, and it goes on to the grid. So this, again, the fuel is free, but you can see that there are some other precautionary measures. You need to be careful about the environment. Also, the area in this would be very dangerous. So flying birds and flying airplanes they would be denied to operate in a large area surrounding this facility. We don't have too many concentrated solar plants, but in Arizona, there's a place called Tonopah, where we have a fairly large project that's being put together. There are regulations in the US market. I'm not very familiar with the Indian regulations, but they have a bidding procedure, so it's very competitive. I think our electricity cost in the US is comparable to in India. So it's very cheap because the cost of living obviously is much higher here. There are tax rebate systems to incentivize building of solar. You have that in India also. And especially for small consumers, systems below 1 megawatt, residential unit facilities and some small companies, small business owners can benefit from net metering system. And I'm not sure what the policies are in India regarding net metering, but we have some very diverse policies. They vary from one state to another, and it would be good to see how India compares with the US and maybe compare it to different states. This is an interesting graph, very busy, but I just want you to focus on the trend in what is called the levelized cost of energy. This is the unit cost for every dollar spent, how many kilowatt hours do you get out of this? So the less money you spend per kilowatt hour, this is very desirable. So you want levelized cost to be below or decreasing, coming down in value over time. And if you look at this graph, you can see that the conventional fuels, fossil fuels for the past decade have been somewhat steady, sometimes going up. For example, here for hydro, geothermal, which is a renewable resource, has gone up for the last decade, but look at solar photovoltaic. It's dropped dramatically from 2009 to where we are today, to 2010 to where we are today, 2019. Same with concentrated solar, same with wind, and same with offshore wind, and same with onshore wind. So very good news. The renewables that are captured here in the levelized cost of electricity are trending in a direction which is very desirable. Less cost per kilowatt hour. And that's what we want. The levelized cost of electricity has come down. I'll talk a little bit about wind energy. There are pros and cons. It requires land that's a little less than solar. And it can be built offshore, and I'll talk a little bit about offshore wind. Offshore wind is very steady. It really doesn't have many environmental impacts, but it does disturb aquatic life, and one needs to make sure that those are being met. But more importantly, the cons. Offshore towers are more expensive, less easy to maintain because you have to go out in the sea. But the advantages are that you get very steady wind offshore, and India should consider this. I'm not sure what the continental shelf looks like on the western side of India, but that could be very desirable to place offshore wind sites there. I'm not going to derive these equations except to say that the kinetic energy in wind generates power which is related to the cube of the velocity that's extracted. That is the difference between the upwind velocity and the downwind velocity is V. Now just think about it. It is the fuel is related to the power is related to the cube of the fuel. Now, which kind of fuel is that beneficial, that generous in providing you power? Well, wind is one of them. And so the larger the diameter of the turbine, the more power you can generate. So that's why today you have turbines that are 250 meters in diameter. That's almost the height of the Empire State Building. They're massive structures. And so you can see that the technology has developed to this point where each wind generator could be 13, 15 megawatts. You know, once upon a time, getting a wind turbine to generate more than 1 megawatt was very difficult. Now you have them generating 15 megawatts or so. This is the curve. As wind speed changes, the power changes exponentially according to the cube of the velocity. Here are some of the, again, equations to look at what is the maximum or what the optimum rotor efficiency. And that's governed by Betz's law. It's a good directive. It can be more than 60% between the difference between the upwind and the downwind velocity. So this is how you determine the optimum efficiency of your wind turbine. And so this graph here shows the Betz limit. And even though the high-speed two-blade seems to be the best according to this curve, there are many reasons where this modern three-blade, I know for dynamic stability, for a host of other reasons, even though it's less efficient, it is more ideal as far as levelized cost of electricity is concerned. So these are kind of what I said when I told you in the beginning about how you need to marry technical knowledge with practical realities. You learn in a curriculum like ours why the modern three-blade, even though it's less efficient than high-speed two-blade, realistically, this is more desirable because the levelized cost of electricity is less than what you have for two-blade turbines. I want to kind of start finishing up. As I said, some of the projects that we have for you to be able to get a master's of engineering degrees through our industry capstone projects. This gives you some of the projects we're working on this academic year. We're looking at intelligent virtual power plants. This is an ongoing effort for the last 2-3 years. Each year, we have a new batch of students working on this project, looking at how you could, through artificial intelligence and machine learning, develop, and I mean this somewhat figuratively, literally, a peak demand asset that could offset actually buying electricity from a vendor that is a central generating station where you end up paying a lot of money. We're looking at the feasibility of solar roofs on warehouses in Pennsylvania. There's been a splurge in building of warehouses, and Pennsylvania has got a pretty medium-based renewable portfolio standard, and there's some potential to increase this by looking at solar on the roof of warehouses in Pennsylvania, PAs in Pennsylvania. Pennsylvania is also a pretty large nuclear generating state. Looking at how nuclear energy could be part of a clean energy system. I'm a great believer that nuclear is clean. We have very good operating experience. And you know, the lifetime cycle cost of greenhouse gas emissions from nuclear is one of the lowest. It is the lowest among all generating capabilities. And so on. So this is a variety of capstone projects we're doing this year. And there's some additional resources from where I got this material. Some of them are presentations that I have made. several papers I have written, but definitely very valuable in ways going forward. I kind of use this as a platform. It is the best time to be in energy for especially the next generation of students coming into this field, and our next generation of students will be working in this field. It's a 10-month, 30-credit program. It's industry-sponsored capstone projects instead of thesis that you normally do in a master's program. It is based on experiential learning. In other words, you have the experience of faculty members who worked in the business, who were able to share what knowledge is. We emphasize hard and soft skills. Leadership requires you know the math and the science and everything else, but also be able to work together in a team. And more, you're going to see this everywhere in the world, working with different people with different backgrounds. And this program is a success, not because I'm saying so. We make it happen. We encircle the ecosystem for teaching with just what we're saying. We have industry that advises us, and we have projects that are based on industry needs. So you're encircled with an ecosystem that is built for student success. And this is what I want to point out. If we've polled students who have graduated, and out of the past decade, 9 out of 10 agree that this is advanced, the program has advanced their career. Again, they're not saying this course was great or that course was great. They're saying in total, 9 out of 10 said that advanced their career. And that is obviously very pleasing news for us. I urge you to go to our website, ese.lehigh.edu, to learn more about it. And if you're interested in applying or inquiring more, just go to this blue button and go from there. But I want to thank you for your patience. I want to thank you for your interest. And for sure, I want you to be the future energy workforce in India. India has got some very ambitious plans. I believe it's one of the most ambitious plans in the world. Next to China. China is already ahead, but India is not too far behind. And we need minds like yours to be able to make it happen. And thank you for your interest. And if you have any questions, please contact Mr. Upadhyaya, who is also one of the hosts in this presentation, or send an email to this the info box within the website. Thank you for your interest again, and Jai Hind.